Welcome to Lecture 4.8, Stability of Face Portraits. So let's summarize what we've learned so far over the last few lectures. So first of all, suppose that we have homogeneous system, x prime equals ax, and let's say the determinant is non-zero. We'll address the case when it is zero shortly. So then there are three general cases. In either one of these three cases, we have real distinct eigenvalues. So this is real distinct eigenvalues. In this case, we have a repeated eigenvalue. Repeated. And in this last case, this is what happens when we have complex eigenvalues. So complex. So in these first two cases, either when they're both positive or both negative, we get one of these. I'm going to sketch it out here. I'm not even going to sketch the axes. I'm going to sketch the eigenvalue lines. They don't necessarily have to be parallel. I guess I didn't quite, or perpendicular. I didn't quite draw them perpendicular, and that's great. So, so we have solutions that are along these lines, and then we have solutions that sort of bend in to the origin. And I'm not going to put arrows on them because the arrows are going out when eigenvalues are positive and the arrows are going in when the eigenvalues are negative. So when we have a saddle point, things are a little bit different. Or I guess I should say when we have this case, one positive and one negative, then let's draw the eigenvector lines as we did before. But now we have and let's say that this one is the positive eigenvalue and this one is the negative. And then we have solutions that go like this way, and then they go this way. And this is, of course, called a saddle. So this is a saddle. I don't really have a name for this one. I think it's called a node. It's not something I ever really use in conversation if I were to teach in class. Of course, I would never call it a node, but I think that's what people call it. Maybe a proper node because there are two eigenvector lines. So let's go to the second case. When you have a repeated eigenvalue, then there are two cases. You either have a star. This one does have a name, although again I don't really use the names for any of these except for saddle. So this is a star. Or the other case is you had one of these things where you have only one eigenvector line, and then you have something like this. This is the annoying case, and as students have pointed out before, this looks sort of like the South Carolina Gamecock logo. So I'll let you decide if there's any meaning in that. This being the obnoxious case, this is called an improper node. And it's obnoxious because there's a lot more work to solve this system when you have a repeated root, as you remember. And finally, the complex case, these things are going to be spirals or ellipses, or some combination like spiraling ellipses. So when A is positive, then we have outward spirals. So these are outward. When A is negative, the spirals are inward. So we have things like something like this. I'm not going to draw an arrow on it, so you can't really tell. Let's see if I can make that a little better. That's fine. And then when A equals 0, they are concentric. Not really sure if I spelled that right, but picture is what matters. Something like this. Okay, so that's a summary as to what the face portraits look like. And again, this is when determinant is non-zero. We'll talk about the case when it is 0 shortly. Okay, so I want to do one example which helps put together what we learned in the previous slide. So this is a one-parameter family of matrices here, or this matrix anyways, and I want to understand what the face portrait of this system looks like as we change alpha. So alpha is now a parameter. So let's first of all compute the eigenvalues and eigenvectors of this. So a minus lambda I I should say the determinant of a minus lambda I. Let me start that over. Sorry, the determinant of a minus lambda I is, let's use my shortcut now, alpha squared minus the trace. The trace is the sum of the diagonal entries, so minus alpha lambda plus the determinant. That determinant is 0 minus negative 4, which is plus 4, equals 0. Let's use the quadratic formula, and we get that lambda 1, lambda 2 is negative b, so that's alpha, plus or minus the square root of b squared, so that's alpha squared, minus 4a, that's 1, and c is 4, so that's 16, all over 2a, which is all over 2. So let me box that, because that's going to be important. So let me write down what I want to do. I want to say, let's vary alpha between plus or minus infinity and see what happens. So let me draw the number line, the whole number, not the whole number line. And so this is the number line. Let me put 0 here. And so I'm going to see what happens so think of this as alpha. So alpha is 0 is here, alpha is 1, alpha 2, alpha equals 3, etc. So what happens? So when alpha is really, really large, like let's suppose alpha is 1,000,000, then this thing is going to be, then this square root is going to be, thing under the square root is going to be positive. So in that case, we have alpha over 2 plus or minus something else. Okay, so notice that this term here, the square root of alpha squared minus 16, is always going to be less than alpha. So note, if alpha is greater than 4, then the square root of alpha squared minus 16 is greater than the square root of alpha squared, which is alpha. Okay? So that means that this number is less than that number. So what we have when alpha is bigger than 4 is we have a big number plus or minus something that's not quite as big. And that means that both of these roots are going to be positive, i.e., and then so that means that lambda 1 and lambda 2 are different, and they're both positive. Because we're starting with alpha and we're subtracting something, we're adding and subtracting something that's less than alpha. So we never get anything negative. So let's draw a 4 up here. So when alpha is greater than 4, so when alpha is in this range, then, so this number line means like alpha. So in this range, lambda 1 and lambda 2 are distinct positive roots. Okay, so what happens when we are at 4? Well, when we're at 4, then this discriminant is 0, so that's when we have a repeated root, alpha plus or minus 0 over 2. So let me do that up here. So at 4 we have lambda 1 equals lambda 2, and lambda 1 and lambda 2 in that case are 4 divided by 2, so that they're actually equal to 2, not like that. I'm not too worried about the exact value. And notice we get the same thing if alpha is negative 4. Well, almost the same thing. So if we have negative 4, then we have a repeated root as well, negative 4 squared minus 16. But now lambda is negative 4 over 2 plus or minus, negative 4 plus or minus 0 over 2. So in this case we have lambda 1 equals lambda 2 equals negative 2. Okay, so what happens? Let's see, what do we want to do? So what happens if we're out in this range? So let's do a symmetry thing. So if we're out, if alpha is less than 4, so let's go up here. So note, if alpha is less than 4, then again, alpha squared minus 16, alpha squared is positive, and this thing, again, is bigger than alpha squared, which is the absolute value of alpha. So if we're over here, now we have a really small number, like say negative 20 plus or minus something that is less than 20. So in that case, both of these roots are going to be negative. So lambda 1 and lambda 2 are going to be different, and they're both going to be negative. So let's write that over here. So in this range, we have lambda 1 and lambda 2 are distinct negative roots. Okay, so now we got to fill in the middle. Let's do 0 first. What happens when we're at 0? When alpha is 0, then the root is 0 plus or minus, let's do this one up, let's write this up here, if alpha equals 0, then lambda 1, lambda 2 is 0 plus or minus, so plus or minus square root of negative 16 over 2. So that is 4i over 2 plus or minus 4i over 2, which is plus or minus 2i. So in this case, lambda 1 and lambda 2 plus or minus 2i, this is when we have purely imaginary roots. So let me say up here, so this is distinct, distinct, D-I-S-T-I-N-C-T, distinct negative. Over here we have distinct positive. Here we have purely imaginary. And then here we have repeated. And over here we have repeated. And the last thing we need to do is figure out what the heck happens in here. So when we're in here, let's see if I'll fit it up here. So if alpha is between 0 and 4 properly, then alpha squared is less than 16. Then, so alpha squared minus 16 is negative, and so this is when we have complex roots. So let me, how do I want to do this? In this region we have alpha 1, 2 is a plus or minus bi. But we also have, I guess I should say, it's not just a plus or minus bi, it's alpha over 2 plus or minus bi. So this value a is positive. So a is positive. Similarly, if we're over here, alpha 1, 2 is a plus or minus bi, and a is going to be negative, because a is alpha over 2 and alpha is negative. So let's sketch what this looks like, or what the phase portraits look like. So over here we have one of these, we have two eigenvectors and we have distinct positive roots. So honestly, I don't know where these things are going to, which direction they're going to bend. If it's going to bend this way or this way. I don't really care. I'm just being qualitative here. So if I got the bend wrong, you're welcome to send me an email and tell me. Maybe I'll change it, but I'm not too worried. I just want you to understand the qualitative nature of these things. And I also don't know where the eigenvectors, what direction they go. So over here we have this proper node where everything goes outward. And over here we have same thing, just everything goes inward. So let me put arrows on. Again, for every value of alpha, we get a different system. So think of like this, and think of this as being a parameter. Like as we tune alpha over here, we're changing the specific eigenvectors, the direction, and also the bend of these lines ever so slightly. But then sometimes we hit these these thresholds where we go from here. We have this improper node. Let's fill this in. So what else do I want to do next? Okay, so here we have purely imaginary roots. That's when we have, I don't know, we have some sort of ellipses. I don't know what direction they go. I don't really care. I'm going to, over here we have, actually right here we have inward spirals. So again, I don't know exactly what the spirals look like. I'm just worried about the qualitative nature. So say this is, so something like this. So these are inward spirals. Inward spirals. Here we have ellipses. Then here we have outward spirals. That's supposed to be, let's make that, there we go. So these are outward spirals. And then we have these two more points here and here. So repeated roots, we have only one eigenvector. This is where we have this South Carolina Gamecock looking node. You know, the annoying one. It's a lot more work. Again, I don't know what the eigenvector is. I don't know if it goes this way or if it goes this way. I don't really care too much, but it's going to go outward. And it's going to go outward, something like this. And over here, we have a similar one. It's just going to go inward. This is that improper node. So this is an improper. And this is a proper node. This is a node. And this is a improper node. So back to what I was saying. Let's suppose that alpha is large. As we make alpha smaller and smaller and smaller, this thing is going to change slightly. The eigenvectors are going to, budge a little bit. The bend's going to budge, and then at some point we get to this like a threshold, a singular point, where this node all of a sudden becomes this improper node. And most likely, as you get closer and closer to here, these two eigenvectors are going to get closer and closer together till they're almost on top of each other. So maybe here you're probably going to get two eigenvectors, I'm guessing, that are like this and this. So they're really close together. And then when you hit 4, they snap together and you get this improper node. And then as you get to the left of 4, this thing becomes spirals. Maybe I would guess that this direction actually should match this direction. So maybe I drew it wrong. So we have spiraling ellipses, and as we move closer and closer to here, those ellipses become more, the spiral becomes less and less until at 0 they become perfect ellipses. And then as we go left of this, the spirals actually, instead of going outward, become inward. So they become inward. And then the same thing here, as we get to -4, the spirals turn into an improper node. And then as we get larger and larger, this one double eigenvector is going to split into two eigenvectors. So just to the left of it is probably going to look something like they're almost on top of each other, but then they pull farther and farther apart, and all of the face portraits in this range are nodes where everything limits toward the origin. The example on the previous slide is actually a special case of a more general setting. So the face portrait of a system x prime equals ax, remember, just depends on the eigenvectors and eigenvalues of A. And the qualitative nature, whether it's a node or a saddle or a spiral or an ellipse, etc., just depends on the eigenvalues of A. So let's suppose that the characteristic equation of A is something like this. This is always the case. And let's call the trace P, and let's call the determinant Q. So every single A can be represented by a pair, P and Q, and for where P is the trace and Q is the determinant, and that A has the following eigenvalues. This is just the quadratic equation. So what we want to do now is I want to actually, instead of sketching like we did in the previous slide, we sketched the number line and it's called that alpha. By the way, that matrix in the previous slide, that would be P would be alpha, and Q I think was 4. So instead of sketching the number line and varying alpha as a single parameter, I want to vary P and Q as 2 parameters. So I'm going to actually sketch the entire plane, the entire PQ plane. Let me call this P. Let me call this Q. And then I want to understand for each point, that's going to represent a whole family of matrices with that same trace and same determinant, whether that point is a spiral, an ellipse, a node, whatever, or what the face portrait is going to be like. And then I want to see the big picture in this plane and how those things all get put together. Okay, so let me start with the special case when we have a repeated eigen value. So repeated eigenvalue, let me write this up here. Repeated lambda 2, that's going to occur when this discriminant is equal to 0. So that occurs when p squared minus 4q equals 0. And let me call this the discriminant delta. So this is actually a degree 2 polynomial on the PQ, the PQ plane. It's the polynomial q equals 1/4 p. So let me sketch that polynomial. I should say it's a parabola. So how do I want to write this? So everything on here, everything on this line corresponds to when we have this is p squared minus 4q equals 0, and this corresponds to when we have a repeated lambda, and so this is when we have that improper node. So let me just write that down. Improper node. Okay, so next, everything that's above this parabola, every pair PQ is going to correspond to when p squared is less than 4q. So that's going to mean that everything under the radical symbol is negative, so we're going to get, so this is going to be an imaginary number, the square root of a negative number, and our eigenvalues are going to be complex. So let me write that up here. So everything up here is complex eigenvalues. Let me put arrows here to signify that I mean everything above here. And conversely, everything below here are going to be real eigenvalues. So let me write that real eigenvalues. And I should say they're complex eigenvalues, and that's because this discriminant, which is p squared minus 4q, is less than 0. So that's why they are complex. And they are real down here because this discriminant is p squared minus, actually I'm going to move it off of this, move it off of the middle. I'm going to put it over here. It's because, well, you'll see why shortly. P squared minus 4q is greater than 0. So that's why there are real eigenvalues below this parabola. Okay, so let's understand this further. If we go, so let's start in this region when we have complex eigenvalues, and let's start when we are on the q-axis. So that happens, this points on the q-axis correspond to when p is 0, which means the real part is going to be 0. So that corresponds to purely imaginary eigenvalues. So points on here, let me change my pen. So points on here are going to be when we have purely imaginary eigenvalues. So points on here are going to be when p equals 0. That's when we have purely imaginary eigenvalues. And so we have ellipses. Okay, so that takes care of these. Now when we're on the right-hand side, everything in here, that's going to be when p is greater than 0. So that means we're going to have outward spirals. So let me draw that up here. So let me draw an outward spiral. So up in this region we have p is greater than 0. So we have outward spirals. Outward spirals. And then over on the left-hand side of the q-axis, we have p is less than 0 because we're over in this range. So we're going to have inward spirals. So let's draw that this way. And so we're going to have p is less than 0. And so we have inward spiral, not in, inward spirals. You may be wondering which direction the spirals go, but recall that every single point is going to correspond to a whole family of matrices with the same trace and the same determinant. And some of those are going to have phase portraits that are spiral counterclockwise, and other will spiral clockwise. So I'm just drawing one direction. The inward spirals are not inward. I'm drawing the counterclockwise direction, but there's going to be, for each point, there's a whole family of matrices. Some of them spiral inward, some spiral outward. Okay, so now that I think we've finished the top half, let's look at the bottom half of not the bottom half, but everything below the parabola, where the eigenvalues are real. Okay, so when we are below, what happens when we're below the p-axis? So we're below the p-axis, q is positive. So everything that is below here, q is negative. When q is negative, that means p squared minus q for q is actually greater than p squared. Let me actually pause to make a comment. So this thing under the square root, if this is greater than p squared, then we're taking p plus or minus something bigger than p, which is going to give us a positive and a negative eigenvalue. However, if the thing under the square root is less than p squared, then we're taking something p plus or minus something smaller than p, so we're going to get two eigenvalues of the same sign. So let me write that up here. So how do I want to say this? So how about up in this corner? Hey, lambda 1 and lambda 2 that are real have the same, let's erase that, have the same sign, SIGN. if and only if p squared minus 4q is less than p squared. Because then, if that's the case, then the square root of that is going to be less than the square root of that, which is going to be p. Okay, so what that means is everything below the p-axis are going to be saddle points. So saddle points. So these are, let me sketch this. This is going to be something like this. And it's also going to be the case on the right-hand side too. So I'm going to put saddle. So let me give myself a little more space. Right over here. So over here, this is going to be saddle points, and it's going to look like. So everything below the p-axis is going to be correspond to a saddle point. Okay, let's go above the. Well, actually, let's go on the p-axis. What happens when? No, let's go above the p-axis. So in here, we're going to have eigenvalues of the same sign, SIGN. And what else? And p is going to be positive. So we have a positive eigenvalue, or positive number, plus or minus something less than p. So we're going to get two. So up here, we're going to get two positive. Actually, let's write it like this: lambda 1 and lambda 2 greater than 0. So we're going to get these nodes. So it's going to look something like. So everything is going to be pointing outward, and then things in the middle are going to bend in one of these directions. So the face portraits are going to look like this qualitatively for all the points in here. For over here, it's going to be a similar thing. But now lambda 1 and lambda 2 are going to be negative. So we're going to get this node thing where everything gets sucked in to the origin. It's going to look just like the other one, just the arrows are going to be reversed. So everything goes inward. Okay, so now what happens when we are on the p-axis? So this happens when q equals 0. So when we are on the p-axis, let's take a little space up here and see what happens. So when q equals 0, that means we have p plus or minus p squared minus 0 over 2. So that means we're going to have p plus or minus p over 2. So that means we're going to have one eigenvalue equal to 0. So I don't know how to draw that, so points that are actually on the p-axis, we're going to have lambda 1 is 0 and lambda 2 is p. So that's going to happen when so this means the determinant is going to be 0. That's the case we haven't really talked about very much. It's sort of in between these two cases, the saddle and the node. And let me finish by looking at this one. When we're here, when we're on the y-axis, but we are, I guess, the q-axis, but below, what's that going to look like? So that's going to happen when p is 0. So now our eigenvalues are going to be 0 plus and minus. So let's do this up here again. So up there we're going to have 0 plus or minus the square root of some negative 4q. And that's going to be actually a positive number because q is negative, divided by 2. So there, actually, we're going to get a plain old saddle point because we have a 0 plus or minus something, which is the square root of something positive, over 2. So this is just plain old saddle as well. So let's write. So to summarize, every matrix in A can be represented by, they're tagged by a pair P and Q. And so this picture here represents all possible matrices, where each point represents a family of matrices. And now you can see, as you move around here, how the eigenvalues change and how each region corresponds to a different family or different qualitative type of face portrait. So the picture that we had on the previous slide, when we had P was alpha and Q was 4, recall that we actually did not get any saddle points for any values of alpha. So what that was is let's take a slice of this, Q equals 4, right here. So if we take this slice of this, then we get a line that we said parameterized by alpha, and we get a region in the middle where there are complex eigenvalues. We get 2 points where there are, let's actually draw this because why not? It's the last thing on the slide. So this is what we did last time. We took a cut right there, and we said let's let alpha vary. And then we had these 2 points where they were repeated. We had this 1 point where there were ellipses, and there's this whole region where we had inward spirals, outward spirals. We had nodes going outwards and nodes going inwards. And so this slide, hopefully you should see why this PQ plane is actually the bigger picture from what we did in the previous slide. Okay, so I want to say a few words about when the determinant is 0, and recall that happens precisely when one of the eigenvalues is equal to 0. The other eigenvalue we don't know. It could be equal to 0, might or might not. So I want to relate this to the previous slide, this PQ plane. So if this is P and this is Q, we have this parabola. And what I want to do is I want to suppose we start up here, and then we move down here, down here. So if we start up here, then this corresponds to a node where there's going to be a bend, something like this. The bend's going to be pronounced. It's going to get less and less as we get toward the p-axis, and then we're down here. It's just going to correspond to some saddle. So maybe this is out and this is in, and maybe it's, I don't know, something like this. So I want to ask what happens. So as we move closer and closer to the p-axis, these bends are going to get less and less, and then I want to talk about what happens when we get really close to the p-axis, or what happens when we get on the p-axis. Let's do that. Yeah. So when we're on the p-axis, we're going to have one of the eigenvalues. So maybe this, let's say it like this. So so with this bend, this is lambda 1, which is, actually, let me call this lambda 1, which is small. Maybe this is lambda 2, and this is large. So as we get down to here, we have a similar thing. We have the eigenvectors like this, and now we're going to have lambda 2 might be large again, and lambda 1, instead of being small, is going to be equal to 0. So now the bend, well, let's draw these little outward things. So over here, these arrows pointed outwards, and over here the arrows pointed inwards. So this is lambda 1 less than 0, and this is maybe lambda 2 large. So over here the arrows pointed outwards, here they point inwards, and here they don't point anywhere at all. So we're going to have, so look something like this. And I want you to really picture how this type of picture is sort of on the threshold between this and on the threshold between that. So I want to finish this lecture with an example of a higher order system of ODEs. I don't want to spend too much time on this, but it's worth seeing because this is going to be a 3 by 3 system, and it's actually going to be nonlinear, so we can't write this using matrices, but it's a very common and very popular model in science, and so I think it's worth spending a few minutes just to show you what it's all about. So this is about disease dynamics, and let's consider an epidemic that spreads through a population. And our epidemic so you can think of it like the flu, you can think of it like Ebola or AIDS or chicken pox. And generally, people are going to be in one of 3 states. Everyone's going to be born susceptible. So let's write this down. So you start susceptible, if I can spell this, that is. Actually, I spelled it below, so yeah, susceptible. And then some people everyone starts susceptible. Some people, when you get sick, you transition into the infected state. And then when you get better, you get an immunity, and you transition into, and you become recovered. So when you have chicken pox once, you can't get it again. Although we've all heard of someone who knows someone who gets it twice. Let's just assume that's not the case. Although you can make more complicated models where people do transition back. But even if it's like the flu, typically you could get the flu several times, but you're going to get different strains in different years. So this one particular flu, once you become recovered, your body develops an immune response and you stay in that state. So this is called the SIR model because SIR. And let's let, at any time t, let's let S of t, I of t, and R of t be the amount of people in each of these states. So initially we have n susceptible, unaffected people, and maybe we have one person who's infected, and then you want to see what happens over time. So let's write down some differential equations for this. And what I want to do is I want to write down a system of 3 differential equations. So let's start out by saying, let's see, so ds dt, and then di dt, and then dr dt. And let's come up with some equations. So you can sort of, in some sense, you can think of this as like a generalized mixing problem because, okay, these things aren't tanks, but these are states, sort of like what tanks are, and you have things that are flowing from here to here. So di dt, the rate of change in the infected people, is going to be the rate in minus the rate out. So we're going to use that idea to write down these differential equations. So ds dt, that's going to be negative because people are always leaving, so the number is going to be decreasing, and so think of it as just rate out. So ds dt is going to be, rate in is 0, no one ever becomes susceptible. We're assuming that people aren't being born, or at least that we're not counting, maybe we're counting a short enough period over time that, well, it's a model, I can say that. We're assuming that people aren't being born. So the ds dt is going to be rate in 0 minus rate out, which is 0 minus. So how many people are leaving? So I'm going to claim that, I'm going to write this as A times S times I. And let me justify this as follows. So I claim that the number of people who become sick, people who make this transition, is proportional to the number of people who are susceptible and proportional to the number of people who are infected. Think about why that makes sense. That means if you double the amount of healthy people in the room, then twice as many people are going to get sick. So if you have one person who's really sick in a room of people, if you double the amount of people who are with them who are susceptible, then you're going to double the amount of people who get sick in the next day. And if you triple the number of people who come in contact with the sick person, you triple the amount of people who get sick. Similarly, it's proportional not only to this, but also to the number of infected people. If you have a room full of healthy people and you double the amount of sick people who interact with them, you're going to double the amount of people who get sick. So when something is proportional to both S and I, we write that as some constant A times S times I. So ds dt is negative AS times I. Okay, so di dt, this is going to be rate in minus rate out. Well, the rate in is just this number, because that's the rate out of this state. So the rate in is A times S times I, and then the rate out, let's just assume that if you got a bunch of people who are sick, you assume that so you have 100 people who are sick, it's safe to assume that some percentage, some fixed percentage are going to get healthy the next day. So let's write that as B times I. So the amount of people who become recovered is proportional to the amount of people who are sick. So let me say a few. So let me say, write this. Say proportional to S of t and I of t. And then for here, let me say this is rate people get sick. This is the rate in minus the rate people get healthy. And then finally, dr dt, if this is, so the rate out of the I state is equal to the rate in of the R state, so this is just going to be B times I. So here is our system. This is nonlinear because of this term here, S times I. So let's write this, actually, let's write this up. So this is S prime equals negative ASI. I prime equals ASI minus B times I. And R prime equals B times I. Here's my system. Let me give it an initial value problem. So we have n susceptible people, and we're assuming that no one is born with the immunity. So in that case, we will have S of 0 equals n. Maybe the number of infected people, that should be, so we should have one initial infected person. This is like agent, or not agent, I guess patient 0. And then let's say no one is recovered. You can, of course, change these. So this is our system of differential equations that we derive. This is nonlinear, but we would still like to be able to analyze this. Now that's beyond the scope of this course. You can take a mathematical modeling course if you're interested in this. Let me say that this is a non-linear, and it's autonomous. There's no T on the right-hand side. Oh, I spelled that wrong. Autonomous, M-O-U-S, system. And so it turns out that if you actually plot so you can plug this into a solver, and let me give you the punchline to this. If you actually figure out what equations solve this, and you plot them, you get something that really does make sense. The number of susceptible people goes down like this. The number of recovered people, so this is S of t. You start out with a lot of susceptibles, and then you go down and people get healthy. And maybe not everybody gets sick. Now, some people, I never had avian bird flu, so I'm one of these people who I'm still susceptible to this day. The people who have not had chickenpox are susceptible to that disease. So this doesn't necessarily go down to 0 unless everyone truly does get sick. The number of recovered people, that's going to start at, eventually nobody's recovered, and that's going to start up here, and that's going to go not quite up to here, because this gap of people, so this is, let me write recovered. This corresponds, so not everyone is recovered. People like me who never got avian bird flu, I'm not recovered, so here's the gap of the people who, so this gap is equal to that gap, and the number of infectious people, think what that looks like. That's going to be some sort of parabola that's going to peak and something like that, and eventually that will go down to 0, because eventually the disease is going to be completely wiped out. And well, I guess it depends on the disease. Something like the flu or chickenpox will be wiped out. If it's something like AIDS, then it's not going to be wiped out. It's going to stay and continue to rise. But this is just a simple example of something that it does a really good job of modeling things like the bird flu or just the standard flu. And as you might expect, people have written thousands and thousands of papers on variations of this. You can tweak this in thousands of ways. You can add a feedback loop back to susceptible. You can add two populations. You can add a population maybe of people and a population of birds or mosquitoes, and they infect each other. Or you can sometimes you add extra states, like you're incubating the disease, but you're not showing symptoms. Some people add so a fourth state. They call it I, for forget what it's called. And then there's thousands and thousands of ways to tweak this, and people still study this to this day. Every time a new infection comes out, whether it's avian bird flu or whether it's a different strain of Ebola, people go back to this model and tweak it, add bells and whistles, and plug it into their computers, and they come out with some. And the goal is to come out with some sort of way to prevent the disease and some way to fight it that we hadn't thought of before.